As you can see, our speaker is already waiting, so हम further delay नहीं करेंगे. We'll just start right away with her introduction. So, hello, Dr. Bilge. I'll be introducing you to the audience now. So, Dr. Bilge Demirköz is a very renowned astroparticle physicist. She teaches at the Middle Eastern Technical University, and she has studied from MIT as well as Oxford University. She has won a number of awards, and she is known for leading the CERN and Turkey collaboration in Turkey. She is spearheading that entire program, and I believe she is a huge inspiration, especially for females. तो खासतौर पे यहाँ पे जो ख़वातीन बैठी हैं, मैं समझती हूँ कि उनके लिए ये एक बहुत रोल मॉडल है, क्योंकि खासतौर पे इस्लामिक वर्ल्ड, शी इज़ अ मुस्लिम साइंटिस्ट, शी इज़ अ वुमन इन स्टेम, और आप सब लोगों के लिए शी विल बी अ ह्यूज इंस्पिरेशन टू लुक फॉरवर्ड टू. सो हेलो डॉक्टर बिल्गे. So, Dr. Bilge, I have very briefly introduced you, which in no way does justice to your immensely impressive profile. I would just request that if you could begin with your presentation and any opening remarks that you have. Thank you very much, Dr. Bilge. Over to you.
Well, it's a real pleasure to be invited to this wonderful event. I am very sorry that I couldn't. So I'm going to talk about that first. So the reason that they're both under the same roof is first, there are a lot of similarity in conditions between space and accelerators. Both have high radiation, vacuum, and high temperature variations. They have very similar, they're very similar in design requirements. They have high electric tolerances, they have fast feedback, low latency and error rates, and they're similar also in operating conditions. And both have limited access, limited data transfer, and also requirements for data processing. The fourth pillar is that safety is really concerned in both environments. Human health and safety concerns are huge in space, and rotors and accelerators as a new long stage lifetime for very expensive equipment. So we first started the lab in 2015 and became a research university center in 2019, and we have about 20 people working at the center. We have a synergy between space and accelerating technologies under the same roof. So what do? We have an experiment up on the International Space Station. It's called LSM'23, and we measure cosmic rays and we search for a signal of dark matter. That's our fundamental science perspective. Next, with the Mentor TBL project, we are doing applied research. We calculate the radiation dose for our national satellites, and we do radiation tests with 15 to 13 milliprotons. And the third thing that we do is we do productive work. We do a lot of science, we do a lot of technique development, so why not go into productive work as well? So we develop some radiation monitors, and we develop shielding materials for space, for hospitals, and for nuclear applications. So our group right now consists of 4 physicists, 5 engineers, 3 technicians, 1 administrative staff, 4 PhD students, and 3 master's students, and maybe you'll become one day. Our group is always looking for great talent. So, how did this field start? Well, this field started because we realized that we were getting cosmic rays from space. So what are cosmic rays? Cosmic rays were discovered right after alpha, beta, and gamma radiation, and cosmic rays coming from space are similar in that way that they are also a kind of radiation. So these are naturally occurring particles coming very close to the speed of light, and mostly they're photons. When these particles come into our atmosphere here at the top, our atmosphere is made of nitrogen and oxygen, so they hit these molecules of, particularly they actually hit the nucleus, and when you hit the nucleus splits, and you get a shadow storm. You get that shadow, the energy transfer of this cosmic ray goes into the nucleus or this proton or this nitrogen or oxygen atom, and then it's like the one particle becomes 20, and then these particles get showered down, and most of them, there are subatomic particles, they stop in the atmosphere. Only a couple reach ground level. But right now, as I speak to you, I'm in Ankara in Turkey, living in Lahore in Pakistan, well, both of us, receive something like 1 million per minute inside our body. And these things go fast, how fast? Very close to the light, faster than 99% of the light. And they are responsible for 30% of the radiation that we receive during our lifetime. So these muons, there are more of them who were to fly. If I could come to Lahore and take a flight, during the flight, the cosmic ray muon flux will increase by about 10%, by about a factor of 10. So when you fly through this part of the shower, and that's why the flight attendants, pilot will receive more radiation than the average population. So what do? We built an experiment that went off to the International Space Station in May 2012. I can't see your hands, but maybe Mosna can help me. So has anyone seen the International Space Station? And those of you who have seen the International Space Station, raise your hand. Alright, I can see a couple of things, I think.
Yes, Dr. Bilge, we can see the International Space Station.
Alright, so how many people have seen it? What percentage of the auditorium in the International Space Station?
Could you guys raise your hands? आप लोग में से किसको इंटरनेशनल स्पेस स्टेशन नजर आ रहा है यहाँ पे? Everyone has almost raised their hands.
Excellent. So I'm very happy because the International Space Station is indeed a very bright object in the sky. And so next time you see it, wait. Today I'm going to tell you about a piece of this International Space Station. It's called the Alpha Magnetic Spectrometer. It is the largest physics experiment up on the International Space Station. And the International Space Station looks like it's quite big. It's about 100 meters from end to end. And here you see it in blue. This is the Alpha Magnetic Spectrometer. So this is a particle physics experiment measuring cosmic rays in space. Why is it called Alpha Magnetic Spectrometer? Why Alpha is the code name of the International Space Station. So when Houston is talking to the International Space Station, they use the code name Alpha. Why is it magnetic? It's magnetic because in a magnet, particles with positive charge and negative charge travel with different curvature, opposite curvature. So we put a magnet up there in space to see particles of opposite charge. And it's called spectrometer because we measure the momentum of the particles that pass through this detector. So let's take a look at it in more detail. Here is the photo that was taken as it was being built at CERN with collaboration. It is an experiment led by MIT, but it's a NASA experiment, so we use feet. So it's 15 feet by 12 feet by 9 feet, so that's about 4 meters by 3 meters by 4 meters. And it's quite big. It's 7.5 tons. That's considered big for a space experiment. And inside it there are 100,000 electron channels and 650 processors to understand data and going through this thing. It went through space with the space shuttle, which is now retired. From Kennedy Space Center in Florida, in the United States. Here you can see it on the launch pad, and AMS is inside a space shuttle. So if you look inside the space shuttle, you see AMS in the dangerous cargo bay. And here's the crew, the STS-134 crew that took us to space in 2012. And here's the launch. So I thought, as an aside, I'd give you a couple of numbers why the space shuttle was retired. So space shuttles are known to be retired because, so I'm going to talk about that first. So the reason that they go under the same roof is first, there are a lot of similarity conditions between space and accelerators. Both have high radiation, vacuum, and high temperature variations. They have very similar in design requirements. They have high electric tolerances, they have fast feedback, low latency and error rates, and they're similar also in operating conditions. And both have limited access, limited data transfer, and also requirements for data processing. The fourth pillar is that safety is a real concern in both environments. Human health and safety concerns are huge in space, and rollers and accelerators as a new one in stage lifetime for very expensive equipment. So we first founded the lab in 2015 and became a research university center in 2019. And we have about 20 people working at the center, and we have a synergy between space and accelerating technologies under the sea roof. So what do? We have an experiment up on the International Space Station. It's called LSM'23, and we measure cosmic rays, and we search for a signal of dark matter. That's our fundamental science perspective. Next, with the mentioned DBL project, we are doing applied research. We calculate the radiation dose for our national satellites, and we do radiation tests with 15 to 13 milliprotons. And the third thing that we do is we do productive work. We do a lot of science, we do a lot of technique development, so why not go into productive work as well? So we develop cell radiation monitors, and we develop shielding materials for space, for hospitals, and for nuclear applications. So our group right now consists of 4 physicists, 5 engineers, 3 technicians, and 1 administrative staff, 4 PhD students, and 3 master's students, and maybe they'll become one day. Our group is always looking for great talent. So, how did this field start? Well, this field started because we realized that we were getting cosmic rays from space. So what are cosmic rays? Cosmic rays were discovered right after alpha, beta, and gamma radiation, and cosmic rays coming from space are similar in that way that they are also a kind of radiation. So these are naturally occurring particles coming very close to the speed of light, and mostly they are photons. When these particles come into our atmosphere here at the top, our atmosphere is made of nitrogen and oxygen, so they hit these molecules of, more particularly they actually hit the nucleus, and when they hit the nucleus splits, and you get a shower started. You get that shower, that the energy transfer of this cosmic ray goes into the nucleus or this proton or this nitrogen or oxygen atom, and then it's like the one particle becomes 20, and then these particles that shower down, and most of them, there are subatomic particles, they stop in the atmosphere. Only a couple reach ground level. But right now, as I speak to you, I'm in Ankara, in Turkey, we're in Lahore, in Pakistan. Well, both of us, we see something like 1 million per minute inside our body. And these things go fast, how fast? Very close to the light, faster than 99% of the light. And they are responsible for 30% of the radiation that we receive during our lifetime. So these muons, there are more of them who were to fly. If I could come to Lahore and take a flight, during the flight, the cosmic ray muon flux will increase by about 10%, by about a factor of 10. So when you fly through this part of the shower, and that's why flight attendants will receive more radiation than the average population. So what do? We built an experiment that went off to the International Space Station in May 2012. I can't see your hands, but maybe Monsina can help me. So has anyone seen the International Space Station? And those of you who have seen the International Space Station, raise your hand. Alright, I can see a couple of things, I think.
Yes, Dr. Bilge, we can see the International Space Station.
Alright, so how many people have seen it? What percentage of the auditorium in the International Space Station?
Could you guys raise your hands? आप लोग में से किसको इंटरनेशनल स्पेस स्टेशन नजर आ रहा है यहाँ पे? Everyone has almost raised their hands.
Excellent, excellent. So I'm very happy because the International Space Station is indeed a very bright object in the sky. And so next time you see it, wait. Today I'm going to tell you about a piece of this International Space Station. It's called the Alpha Magnetic Spectrometer. It is the largest physics experiment of all the International Space Station. And the International Space Station looks like it's quite big. It's about 100 meters from end to end. And here you see it in blue. This is the alpha magnetic spectrometer. So this is a particle physics experiment measuring cosmic rays in space. Why is it called alpha magnetic spectrometer? Why alpha is the code name of the International Space Station. So when Houston is talking to the International Space Station, they use the code name alpha. Why is it magnetic? It's magnetic because in a magnet, particles with positive charge and negative charge travel with different curvature, with opposite curvature. So we put a magnet up there in space to see particles of opposite charge. And it's called spectrometer because we measure the momentum of the particles that pass through this detector. So let's take a look at it in more detail. Here is the photo was taken as it was being built at CERN with collaboration. It is an experiment led by MIT, but it's a NASA experiment, so we use feet. So it's 15 feet by 12 feet by 9 feet, so that's about 4 meters by 3 meters by 4 meters. And it's quite big. It's 7.5 tons. That's considered big for a space experiment. And inside there are 100,000 electron channels and 650 processors to understand data and through this thing. It went through space with the space shuttle, which is now retired. It flew from Kennedy Space Center in Florida, the United States. Here you can see it at the launch pad. AMS is inside a space shuttle. If you look inside the space shuttle, you see AMS in the Davis cargo bay. And here's the crew, the STS-1034 crew that took us to space in 2012. And here's the launch. So I thought, as an aside, I'd give you a couple of numbers why the space shuttle was retired. So space shuttles are no longer flying because the SpaceX and other companies now have changed this mathematical equation of taking it into space. So here is a later was the rocket that flew went up like a rocket that actually landed like a plane. So this Endeavour that carried these astronauts was 110 tons at liftoff. The external tank, which is this orange tank that is attached to, that carried oxygen and hydrogen and burnt directly to water, was 756 tons. The two SRBs, what you can see back here, the other ones here, the solid rocket boosters on the side, 1,142 tons at liftoff, and the total weight was about 2,008 tons at liftoff. And what was the goal was to take AMS with a weight of 7.5 tons to space. So what's now happening in new technology developed by several companies is that this ratio, the total weight at liftoff versus the weight of your payload, that ratio is actually being disrupted, and that's why the space shuttle has now retired. And what we do now is we carry the payload separate from the crew. So the idea here was that the crew would fly together with the payload, and this made the payload, the requirements on the payload heavier. Now they're separate, so you carry payload separately and you can carry the crew separately, and this actually eases the requirements on payload. So that's why the discussion in space has come from. So if I continue, here's the launch on the 16th of May 2011. Here it is from Kennedy Space Center during the day. And then we were installed on the International Space Station on the 19th of May, and you see us sitting up there since now 12 years. We've been collecting data since 12 years. We've collected a lot of data. So who are we? Well, we are an international collaboration led by MIT in the United States, but we have 18 countries that are a member of the collaboration. Here we see Turkey and my institute, METU, Ankara, as a member of the collaboration. We often meet at CERN in Switzerland for our collaboration meetings. I was there about a month ago for a collaboration meeting. I come and go often to CERN. And as you know, CERN is the home of the Large Hadron Collider, but CERN houses a lot of experiments also from outside of CERN, and we are a recognized experiment for CERN. AMS is luckily controlled also from CERN. Its control center is not at Houston. It used to be at Houston. It was at Houston for about a month, and then they let us carry the control center to CERN. So this is what is known as the CERN POP. POP means Payload Operations and Control Center. So we have a control center where we control, monitor each piece of equipment. So I'm going to talk about that first. So the reason that they're both under the same roof is first, there are a lot of similarity in conditions between space and accelerators. Both have high radiation, vacuum, and high temperature variations. They have very similar in design requirements. They have high electric tolerances, they have fast feedback, low latency and error rates, and they're similar also in operating conditions. And both have limited access, limited data transfer, and also requirements for data processing. The fourth here is that safety is really concerned in both environments. Human health and safety concerns are huge in space, as well as in accelerators, and you want to save lifetime for very expensive equipment. So we first started the lab in 2015 and became a research university center in 2019, and we have about 20 people working at the center, and we have a synergy between space and accelerating technologies under the same roof. So what do? We have an experiment up on the International Space Station. It's called AMS'23, and we measure cosmic rays, and we search for a signal of dark matter. That's our fundamental science perspective. Next, with the mentioned DBL project, we are doing applied research. We calculate the radiation dose for our national satellites, and we do radiation tests with 15 to 13 milliprotons. And the third thing that we do is we do productive development. We do a lot of science, we do a lot of technique development, so why not go into productive development as well? So we develop cell radiation monitors, and we develop shielding materials for space, for hospitals, and for nuclear applications. So our group right now consists of 4 physicists, 5 engineers, 3 technicians, 1 administrative staff, 4 PhD students, and 3 master's students, and maybe it will become one day. Our group is always looking for great talent. So, how did this field start? Well, this field started because we realized that we were getting cosmic rays from space. So what are cosmic rays? Cosmic rays were discovered right after alpha, beta, and gamma radiation, and cosmic rays coming from space are similar in that way that they are also a kind of radiation. So these are naturally occurring particles coming very close to the speed of light, and mostly they are photons. When these particles come into our atmosphere here at the top, our atmosphere is nitrogen and oxygen exposure increases. Whereas our satellites are often we want them to be as light as possible, as thin as possible, materials outside them to be as thin as possible. So this means that lots of satellites are receiving hundreds of kilograms in their lifetime. So, and that's deadly. That would be a deadly thing for humans. So how do satellites actually fight this? So there are a couple of things that you can do. First thing you can do is you can test them against radiation before you send them to space. So we built a facility in Turkey with CERN collaboration to test electrons against space radiation. So we have a Cyclone 30, it's a 30 MeV proton accelerator. Here is the accelerator, and here we are on this arm. So it has 4 arms, and the other arms are there for radiopharmaceutical production. So here we are in this room. Here's the design. We have 15 to 30 protons, and we built this arm. Mostly done, everything was done in Turkey. We have a beam which comes in and it's really thin like a hair strand, like at the LSM', and then we blow it up. We blow up the beam in X and Y. We blow it up in so as it's going like this, we blow it up and make it bigger, so that at the end it's the size of an A4 paper, and now we test electronics with it. So we have many subsystems. So in Turkey, for the first time, we built a proton beam line. We studied beam optics. We built a vacuum system. We built a robotic system. We developed a test and measurement system with CERN's help. We developed our own control and cooling system. It was done all in-house with Turkish engineers and physicists. And this facility is now working. We're delivering at the end of this beam line. We have an area the size of an A4 paper, and we deliver here 15 to 30 MeV protons, and we mimic the space radiation environment. And we give pieces of satellites, pieces of electronics of spacecraft, equivalent radiation that they would receive in 10 years in orbit in about a couple of hours, and then we test to make sure that they withstand this amount of radiation. So why is that important? That's important because now we know that we're going to be able to use that electronics for 10 years in space, and that's very valuable information. So we tested about 100 electronics cards using this facility. And if there's anyone in Pakistan, we're more than happy to invite you to this facility to test your pieces of electronics from Pakistan as well. So here is the uniformity of the target area at about 6%. And you can see here, so there's something called gaphron film. And when this gaphron film sees radiation, there's a shadow left by a proton. Here you can see the shadow left by a proton on this gaphron film in a couple of minutes. And we have our proton flux adjustable to the user's needs. So that was the first thing that we did to show that while we do work to photograph matter, the knowledge that we develop from understanding cosmic rays in space is actually useful for society, for our spacecraft. The other thing we've done is we're developing radiation shields for satellites to actually let them live longer in space. And the third thing that we do is we're building a database of electronics and that we know are working in space since a long time, and that helps you, that helps us, that helps everyone design better for space. What I want to better is money more robust and things that will last a longer time. The crown jewel of what we've done is we've designed industrial science particle microscopy and produced it and tested it, and we're using it now. And this company that we helped learn how to build a magnet is now selling magnets to CERN. And lastly, when you go to space, as you go to space, the dose rate increases. So on this x-axis, you see the dose rate in black, you see the flux in red, and you see the effective dose in blue, and on the y-axis is altitude. And here, as you see, as you go from about 1 kilometer up there to here, the data finishes at 37 kilometers. You see, there's a very funny thing. You see that around 20 kilometers there is a maximum, called the physicist maximum. And the reason is, remember this shower? The shower actually has a maximum. So the number of particles, when the cosmic rays come and hit the Earth, the the multiplicity of particles increases at about 20 kilometers, and then they decay, and you can see them decaying down to Earth level. And so the balloon flights give us data up to 37 kilometers, and then there is no data from 37 kilometers up to satellites in orbit. And then, when you're in orbit, you have some data from the International Space Station, and you have this hunchback. Remember the hunchback? Here's the hunchback as you go to higher and higher altitude. And here is the innermost radiation belt, here is the outer radiation belt, and then here is data finally taken from the moon. So why is there no data here? Because between 37 kilometers and about 300 kilometers, the only things that are there are rockets. So since there was no data here, we thought, okay, we'll do something about that. Turkey has now a rocket program that reaches orbit, or will reach orbit in 2 years. So we have a program for responding rockets. So we built a radiation monitor with Geiger counters and photon detectors inside. So here's our prototype radiation monitor, and we flew this thing twice in rockets. And we're about to fly, we're hoping to fly another one soon. So that's the other thing we do, and then we want to fly these things on satellites to understand how much radiation a satellite receives to be able to predict when the satellite goes off. So all of these things were possible because of the associate membership of Turkey to CERN. Pakistan followed Turkey closely, and Pakistan also happily became associate member to CERN a couple of years after Turkey. So it's really great to be collaborating with you at CERN as well. Here is the signing ceremony in 2014. Here's the government decree in 2015 to make us associate member. So we've been an associate member to CERN since 8 years, and we have benefited greatly from the knowledge and technology transfer from CERN in what we've done. So lastly, I would like to mention that I haven't done all of this by myself. It's really a group effort. I have lots of really happy, smiling students, as you see here, technicians, engineers. We work very closely with also biologists to understand biology effects. And then we often ship our students off to prestigious universities, and then they come back later. And I think this is the way of science. We collaborate, we work together, and we're a lot of community. So I would like to thank our supporters at the Ministry of Development and Tamam Nuken, the accelerator in Turkey. And I would like to thank you very much for spending your Saturday morning with me, the earliest session possible. But I don't hear you. I saw you clapping, but I didn't hear you clapping. So
I'm sorry I don't understand what you're saying, but thank you, Dr. Bilge. She's asking if anyone has any questions, then we can take those questions as well right now. So kindly let us know if anyone has any questions, you can raise your hand. I guess everyone is very eager to see the outside Lahore Science Mela. Okay, we have one question from our president, Dr. Shahid Ali.
Hello. Yeah. Thank you, Professor. Very nice, very informative talk. Hello, Professor. Can you hear me?
Yes, I can hear you.
Actually, here in our auditorium, most of the audience are high school students and some from intermediate colleges. So I assume if you kindly express some views, what is the scope of science, research, particularly astronomy and space science, for the students to adopt as a career, and what are the benefits of choosing astronomy as a career? So kindly a few words on this, please. Thank you.
Well, I'm not an astronomer. I'm an astroparticle physicist, which means that I'm really a particle physicist, but the environment that I work in is in space. And the thing that I can say about why I love working in space is because it's the combination. It's an interdisciplinary area. So I get to talk to astronomers, I get to talk to particle physicists, I get to build really cool detectors, and it gives me a perspective on the universe as it was built, as it was created, and I'm very excited about figuring out more about the universe. Dark matter is one of the biggest puzzles of the universe. We don't yet understand dark matter, but I hope that in our lifetime we will be able to understand dark matter, as is most of the matter in the universe is dark matter. So that's really exciting. The pursuit of something new.
Okay, thank you, Professor.
Thank you.
Thank you, Dr. Bilge. I think you will also be very pleased to see Joe sitting right there. We are very glad that Joe could come at the reunion. Yeah. So, if there are any other questions, you can raise your If there are any other questions, you can raise your hand.
Can you hear me?
Do we have one more question from Pakistan Atomic Energy Commission?
Many thanks for very good talk. I have a question. Turkey is building its own accelerator. It is for what purpose? For medical applications or other things? But up to which energy maximum they want to go for this accelerator?
So this proton accelerator that we are working on was built by IBA, Belgium, but the beamline. So let me show you. Let me go back. So this accelerator, the Cyclone 30 proton accelerator, can go up to 30 MeV. It's built by IBA, which is a company in Belgium. What we built, so this was as built. And then we built this arm. So we built this whole thing. This arm is what we built in Turkey by ourselves and with shared support. So this goes up to 13 MeV. So now there are several plans to build other accelerators in Turkey, but one of them that's being built is Hala, and that's an electron accelerator that will go up to a couple of GeV. I'm not involved in that effort, and I don't want to mislead you, but I can, if Monsina will please connect me and you, I'm more than happy to write to the leader of the project, the director of the project, and talk to them directly.
Thank you, Dr. Bilge. I will make sure to connect you with Dr. Zafar, who is also the representative of Pakistan to CERN. So Joe already knows, and I also connect both of you as a discussion. So once again, a heartfelt thank you to you, Dr. Bilge, a heartfelt thank you to everyone who came in this session, and we're immensely grateful to you for sparing the time, and obviously would have been more amazing if you would have come to Lahore, but we're hoping that we can host you next year. So thank you once again, Dr. Bilge, and thank you everyone.